Hello everyone, welcome to the 7th tutorial of this course. In this tutorial I will be solving assignment 7 from the course of 2021. If you have any doubts regarding the lectures, you can ask me in the comment section or you can unmute yourself and ask. Let me share the screen. Okay, so I have shared the screen. The problem 1 is we are asked to find out the area of the ellipse cut from the plane z equals to x by the cylinder x square plus y square equal to 1. So let's draw the cylinder and the plane and let's see how the ellipse looks. So let's say this is our cylinder and the plane is z equals to x. So that means in this xz plane it will cut it like this. So it will basically look like this. Now if you see, the plane will cut this cylindrical region in this way. So basically we are asked to find out the area of this elliptical region. So now let's parameterize this surface. So as there is given a cylindrical equation of a cylinder, then so equation of the cylinder given is x square plus y square equals to 1 and the plane is z equals to x. So basically, in order to cover this entire surface, so for the x and y coordinate, so as it is satisfying equation of a circle basically, so in xy plane, so in that case we will parameterize it like x equals to some rho cos phi and y equals to rho sin phi. So basically let's say it is the xy plane, and if this is the sorry so if this is a circle of radius rho, let's say, so in that case this is the radius rho and this is the phi. So then the x component will be rho cos phi and y component will be rho sin phi, and then the z from this equation of the plane, z equals to x. So then z equals to x means rho cos phi. So with this xyz coordinate, if we put any value of rho and phi, we will be at some point on this elliptical surface. So this is basically parameterization of this elliptical surface with parameter rho and phi. So then our radius vector, or let's say r, which is a function of rho and phi, it can be written as xi hat plus yj hat plus zk hat, which is rho cos phi I hat plus rho sin phi j hat plus rho cos phi k hat. So now to calculate the area, we need to consider a small area element. So let's say this is ds. So the area will be integration of this ds over this elliptical region. So now this ds can be written as phi rho cross phi of small phi mod of that times d rho d phi. And this phi rho cross this phi of phi, it can be calculated from this equation xy del rho phi square plus del of yz del rho phi mod square plus del of zx del rho phi mod square. Now if you do that, so determinant of this Jacobian del xy by del rho phi, it will be so the first element will be del x del rho. So this is the x rho cos phi, so del x del rho will be only cos phi. The second element will be del y del rho, and y is rho sin phi, so del y del rho will be just sin phi, and then here it will be del x del phi, so x is rho cos phi, so it will be minus rho sin phi. Similarly here it will be del y del rho, and y is rho sin phi, so it will be rho cos phi square plus so here it is del y del rho, first element, and del y del rho is sin phi, then it is del z del rho, and del z del rho is cos phi, so z is rho cos phi. and then del y del phi is rho cos phi, and del z del phi, that is same as del x del phi, so it will be minus rho sin phi square plus, so here we have, so this is we have del x, this is we have del z del rho, this is we have del z del rho, del x del rho, and del z del phi, and del x del phi mod square. Now z and x are same, so z and x are same because we are in z equals to x plane. So in that case, these derivatives del z del rho and del x del rho, that will be equal, and this del z del phi and del x del phi, that will also be equal. So determinant of that, it will be 0. So in that case, it's rho cos square phi plus rho sin square phi square plus minus rho sin square phi minus rho cos square phi and square of that. So now if we take this rho common, it will be sin square phi, sin square phi plus cos square phi, and that is 1. So it will be root under rho square plus, again here is also, it is, if we take this minus rho common, it will be sin square phi plus cos square phi. So that's 1, and it will be rho square. So it will be twice rho square, that means root 2 rho. So then the area will be, area of this elliptical region, it will be surface integral of this quantity we already calculated, that is root 2 rho. So root 2 rho d rho d phi, root 2 rho d rho d phi. And now to cover the whole area, this rho should be varying from 0 to 1. That will cover the entire area of this ellipse. So the rho should be varying from 0 to 1, and phi, this angle, should be varying from 0 to 2 pi. It will cover this whole range. So rho should be varying from 0 to 1, and phi should be varying from 0 to 2 pi. So in that case, 0 to 2 pi, you can take root 2 outside. So then it is integration from 0 to 1 rho d rho d phi, which is 0 to 2 pi rho square by 2 from 0 to 1 d phi. So if we put the limit, it will be half. So we have root 2 by 2, 0 to 2 pi d phi, and if you do the integration, d phi integration is phi, and if you put the limit, it will be 2 pi. So root 2 by 2 times 2 pi equals to root 2 pi. So that's the area. So that's the area of this elliptical region. So the correct option is the option 2. So now in problem 2, we are asked to find out the area of the portion of the paraboloid, and the equation is given by x equals to 4 minus y square minus z square, and that lies above this ring, and the ring is so 1 greater than less than equals to y square plus z square, and less than equals to 4 in the yz plane. So let's draw this region first. So this is the yz plane. So then the ring, so this is basically in this yz plane, this is basically the radius of the ring. So let's call it rho square, radius square. So the radius should be then, the radius of the ring in this yz plane, it should be, so rho should be between 1 and 2. So let's say this is a circle of radius 1, and let's say this is a circle of radius 2, and let's say this is the z axis. So the ring is this one. So inside these two circle, the region inside these two circle. So and if you draw the paraboloid, then it will look like, so when yz equals to 0, then x equals to 4. So let's say, oh, sorry, this is the x axis. So let's say this is x equals to 4. So it will start from here and it will gradually go like this. So the surface should look like this. And we are asked to find out the area of the portion that is above this ring. Okay, so then this portion should be excluded. Like let's say if we draw a perpendicular along the y-x axis, then it will, so this kind of portion will be excluded. So and apart from that, the rest area we have to calculate. So then let's parameterize this surface. So the equation of parabola, that is given as x equals to 4 minus y square minus z square, and so let's call this, so in this yz plane we are basically we are covering basically circular regions. So in that case, the correct the easier way to parameterize the surface is basically first parameterize this x in this x z coordinates. So in that case, let's call x as rho cos phi, sorry, y. So why you are doing that? It's because in this yz coordinate, we are basically in this yz plane, we are basically inside this ring like region. So where it is basically inside, we are in between two circles. So if this is rho and this angle is phi, so in that case y will be rho cos phi and z will be rho sin phi, and from this equation of this paraboloid, x will be 4 minus y square minus z square, that is if we take rho square common, it will be sin square phi plus cos square phi, and that is 1. So it is 4 minus rho square. So that's the parameterization. So basically we are expressing this xyz coordinate, or let's say any point on this paraboloid, by this rho and phi coordinate. So then the radius vector in terms of rho phi, it will be, let's call it capital phi, it will be x I hat plus y j hat plus z k hat. This radius vector gives any point on this paraboloid. So it will be rho, it will be 4 minus rho square I hat plus y is rho cos phi j hat plus z is rho sin phi k hat. So again we need to find out the area, which is integration ds, where ds is any small surface element. So like this, any surface element on this paraboloid. So it is given by then integration modulus of phi rho cross phi of small phi times d rho d phi. So now we need to calculate this quantity. So this quantity is given by root under mod of del of x y del of rho phi square plus del of yz del of rho phi square plus del of zx del of rho phi mod square. Now if you calculate these determinants, it will be determinant of, so the first element is del x del rho. This del x del rho is, so x is 4 minus rho square, so del x del rho will be twice rho, sorry, minus of 2 rho. Then the second element will be del y del rho, and y is rho cos phi, so it will be cos phi only. Then here we have del x del phi, so x has no phi dependence, so it will be 0. And the last element will be del y del phi, and del y del phi will be, so y is rho cos phi, and del y del phi will be minus rho sin phi. Determinant and square plus, then the first element will be del y del rho, so del y del rho is cos phi, then this is del z del rho, is sin phi because z is rho sin phi, and then we have here we have del y del phi, so del y del phi is minus rho sin phi, and here we have del z del phi, that is rho cos phi, determinant of that square, plus again here the first element will be del z del rho, and del z del rho already calculated here, that is sin phi, so this term is the del z del rho, so it is sin phi, and then next term is del x del rho, this term is the del x del rho, so it is minus 2 rho, and then the next term is del the next term is del z del phi, so del z del phi is rho cos phi, this term, this is rho cos phi, and del x del phi, and this del x del phi, there is no phi dependence in x, here there is no phi dependence in x, so that means it is 0, square of that. Now if you calculate it, it will be, so it will be 4 rho square, sorry, rho to the power 4 sin square phi plus, so this is rho cos square phi plus rho sin square phi, and square of that. So if we take this row common, it will be rho square out. If we take outside this square, and this cos square phi plus sin square phi, that is 1. So it will be simply rho square plus here we have 4. So this term will be 0, this multiplication, and we have this, then 4 rho to the power 4 cos square phi. So then what we have is, so if we take these two terms, this term and this term, and this take 4 rho to the power 4 common, so it will be sin square phi plus cos square phi, and that is 1. So we have 4 rho to the power 4 plus rho square, and then if we take this rho square common, so it will come outside as rho, and inside this root we have 4 rho square plus 1. Okay, so then the area will be, integration of this quantity. So this quantity is rho 4 rho square plus 1 times d rho d phi. And now here to put the limit, so we are in this EA region, in this ring, inside this ring, and here the rho is varying from 1 to 2. So the limit of rho is from 1 to 2, and the limit of phi, so phi, to cover this entire ring, phi should go from this 0 to 2 pi. It should rotate the whole plane. So then the limit of phi will be 0 to 2 pi. Now if you do the integration, it will be, so there is no phi dependency here, so we can take this phi outside this rho integration, and we can integrate it separately, and then this term will be from integration from 1 to 2 put under 4 rho square plus 1, and d of, let's put it 4 rho square plus 1. So in that case, if we do this d of 4 rho square plus 1, we will have 8 rho, and we have only 1 rho here. To match that, we need 1 by 8. So if you calculate 1 by 8 times d rho square plus 1, it will be rho times d rho. So we are basically writing this in place of this, and this integration is 2 pi. So basically we have 2 pi by 8, this 8, integration, okay, from 1 to 2 put under 4 rho square plus 1 d of 4 rho square plus 1. So it will be pi by 4 times, so we can treat it as a single quantity, let's say x. So it is x to the power half dx. So integration of that will be plus 1 whole to the power 3 by 2 by 3 by 2, and limit is from 1 to 2. So it will be pi by 6, and if you put the upper limit, it will be, so 4 times 2 square, that is 4. So 16 plus 1, 17 to the power 3 by 2 minus lower limit. The lower limit will be, if you put 1, it will be 4 plus 1, so 5 to the power 3 by 2, which is pi by 6, 17 root 17 minus 5 root 5. That's the area. That's the area of this paraboloid portion, which is above this ring. So the correct option is the fourth one. And the third problem, so we are asked to find out the area of the portion of the plane y equals to 2 y plus 2z equals to 2 inside the cylinder of this x square plus y square equals to 1. So it's similar problem like we did in the first one. So here we also have a cylinder of radius 1. So let's draw it. Is x, y and z. So here we basically have a cylindrical region like this, and this plane, that is y plus 2z equals to 2. That means this is 1 and this is 1, because the cylinder, so in this xy plane it's a circle of radius 1, and this plane, so it cuts the y axis at 2 and cuts the z axis at 1. So this plane will look like this. So in this yz plane it's a line, and now if you extend in in the x axis, then it will look like a plane. So again it will cut this cylinder in a elliptical region. This is the portion the cylinder cuts from this plane. So we are asked to find out the area of this region. So this is the area we are asked to find out. And now, so let's parameterize this plane. So we are inside this cylinder. So again we will parameterize it like x equals to rho cos phi and y equals to rho sin phi, and then the z will be from this plane equation. The z will be from this plane equation y plus 2z equals to 2, right? Yeah. So then z will be 1 minus y by 2. So it will be z will be 1 minus y is rho sin phi, so rho by 2 sin phi. And with this parameterization, so basically for each value of rho and phi, if we put this x, y, z, so then the radius vector, or let's say capital phi of rho phi, it will be x I hat, that is rho cos phi I hat plus rho sin phi j hat plus 1 minus rho by 2 sin phi k hat. So this is any position on this plane. So if you put any value of rho and phi, we will be at some point on this plane, on this elliptical plane, area of which we are asked to find out. So again the area will be integration ds, surface integration ds, where ds is a small element here, and this ds can be written as mod of phi rho cross phi phi d rho d phi. So we basically need to calculate now this quantity, phi of rho cross phi, mod of that it will be root under del xy, determinant of this Jacobian, rho phi square plus del of yz del of rho phi square plus del of zx del of rho phi square. The first determinant, the first element will be del x del rho, and x is rho cos phi, so del x del rho will be cos phi. Then the second element is del y del rho, y is rho sin phi, so del y del rho will be sin phi. Then here we have del x del phi, del x del phi will be minus rho sin phi, it will be minus rho sin phi, and del y del phi it will be rho cos phi, because y is rho sin phi square plus determinant of first element will be del y del rho. Del y del rho we already calculated here, that is sin phi. This is the del y del rho. Second is del z del rho. Del z del rho is, so here if we take del z del rho, it will be minus half sin phi, so it will be minus half sin phi. And then del y del phi is this term, that is rho cos phi, and del z del phi, if you calculate it here, so it will be minus rho by 2 cos phi, minus rho by 2 cos phi mod of that square, determinant of its square. And now the first term will be del z del rho, so this is the del z del rho term, that is minus half sin phi. The second term is del x del rho, so del x del rho is this term, that is cos phi. Now here we have del z del phi, this is the del z del phi, is minus rho by 2 cos phi, and the third one is the fourth one is del x del rho, and this is the del x del rho, so we have minus rho sin phi, sorry, this is del x del phi square. Now if we calculate it, it will be, so rho cos square phi plus rho sin square phi, and sin square phi plus cos square phi 1, so we will have rho square plus, so here we have minus rho by 2 sin phi cos phi, and plus rho by 2 sin phi cos phi, so it will be 0, and the last term is so rho by 2 sin square phi plus rho by 2 cos square phi square of that, so this term will be 0, this term will be rho by 2 square, which is rho square by 4, so basically we have rho square plus rho square by 4, which will be rho square by 4 times 5, and root of that will be rho by 2 times root 5. So we have calculated this quantity, so then the area will be double integration of this term, that is rho by 2 times root 5 and d rho d phi, and now rho is so here we are inside this cylinder, so that means rho should go from 0 to 1, because the radius of the cylinder is 1, and we are inside it, so rho should go from 0 to 1, and to cover this entire region the phi should go from 0 to 2 pi, so the limit is 0 to 1, rho is going from 0 to 1 and phi is going from 0 to 2 pi. So there is no phi dependence. We can do this phi integration separately, and integration of d phi is phi. If we put the limit, it will be 2 pi. You can take this constant outside, root phi by 2, and then the integration of 0 to 1, rho d rho. So it is pi times root 2, and if you do the integration, it will be rho square by 2 with lower limit 0, upper limit 1. If we put the limit, it will be half. So then we basically have root 5 by 2 times pi. So that's the area of this elliptical region. So the second option, pi times root 5 by 2. So now the fourth problem. The fourth problem is, so we are asked to find out this surface integration of this vector quantity, and the surface is given by the sphere. So basically, and in the first octant, so we are basically inside this region, so x, y, z. So here we are, and so any normal vector outside this plane, let's call it n hat. The n hat should be radially outward because we are on a sphere. We can calculate n hat by so let's say for any plane, if we want to calculate any normal vector, the equation of this plane will be f of x, y, z equals to x square plus y square plus z square equals minus 9 equals to 0, and the divergence of f, it will be 2x x plus 2x y plus 2x z. So and this sorry, so 2x x I hat plus 2x y j hat plus 2x z k hat, and this is a vector which is perpendicular to this surface. So if you want to find out a normal vector to any surface, then take the divergence. Okay, sorry, it is gradient. I think I am confusing between divergence and gradient. And if you want to find out the unit vector, it will be just if you divide by the amplitude. So it will be x I hat plus y j hat plus z k hat by x square plus y square plus z square. This is the unit vector on this sphere. So then f dot ds integration, so it will be f dot n ds, and f is given by z k hat. So in that case, this f dot n, it is given by, so z k hat dot this term, so then it will be z square by root under x square plus y square plus z square. And now let's find out this ds. This ds is basically phi So to find this ds, we need to first parameterize this surface. So as we are in a sphere, the parameterization is x equals to, so we are in a sphere. So then if any point on the sphere is given by this r vector, then if this angle is theta, and if we take the projection on this plane, if this angle is phi, x, y and z, then x will be r r sine phi, sine theta cos phi, y will be r, so this is the r sine theta, and we are taking the position on the x axis, so it will be r sine theta cos phi, along y axis it will be r sine theta sine phi, and z will be r cos theta. And here we are on this sphere of radius 3, this is 3 square 9, so then r is 3. So basically for our case the correct parameterization will be x equal to 3 sine theta cos phi, y equals to 3 sine theta sine phi, z equals to 3 cos theta. So then phi of theta phi, it will be 3 sine theta cos phi I hat plus 3 sine theta sine phi j hat plus 3 cos theta k hat. So then ds is phi theta cross phi phi d theta d phi. So now we need to calculate this quantity. So then this quantity phi theta cross phi phi, it will be root under, so I am calculating it directly. So the first term will be del x, so this is the x, so del x del theta, so it will be 3 3 cos theta cos phi. The second term will be del y del theta del y, this is the y, so it will be 3 cos theta sin phi, and here it will be 3 this is the del x del phi, so it will be 3 sin theta, and there is a minus sign sin phi, and the fourth term will be del y del phi, that is 3 sin theta cos phi square plus. So similarly if you calculate the other terms, there will be the other terms, so then it will be, the value of it will be, so I have already calculated it, so the value of it will be root under 9 square times sin square theta cos square theta plus sin to the power 4 theta sin square phi plus sin to the power 4 theta cos square phi. And now if you simplify it, it will be 9 times sin theta. So here if you take sin to the power 4 common, it will be 1, and if you take sin square outside, it will be 9 times sin theta. So that's the value of this quantity. So then if you put everything here, so then f dot ds will be f dot n hat times phi theta cross phi phi d theta d phi, so it will be f dot n hat, so f dot n hat is z square by this quantity, and this quantity is so as we are on this surface of this sphere, so this quantity is the radius vector, and that is 3, so we have z square by 3, so z square by 3 f dot n, and this quantity is 9 sin phi, this quantity is 9 sin theta, sorry, so 9 sin theta, and then we have d theta d phi. And now if we replace z by this theta phi, then z is 3 cos theta. So that means z square is 9 square, 3 square, that is 9 cos square theta. And now let's put the limit of integration. So theta is, so we are in this first octant, so that means this theta, so this theta is varying from here to this xy plane, that is pi by 2. So theta is varying from 0 to pi by 2, and phi is varying from this xz plane, so here to this y axis, so that is again pi by 2. So theta, so phi is also varying from pi by 2, 0 to pi by 2. So that means limit of theta from theta is from 0 to pi by 2 and phi is from 0 to pi by 2. So then it will be 27, put 27 outside. So there is no phi integration here, phi term here, so we can put this phi outside of this theta integration and do this phi integration separately. So if we do it, it will be pi by 2, and then the theta integration, it will be 0 to pi by 2 cos square theta, and d of sin theta d theta, we can write it as d of cos theta times minus 1. So if you do d of cos theta, you will get sin theta minus, if you get minus d cos theta, you will get sin theta d, sin theta d theta. So then it will be minus 27 by 2 pi cos cube theta by 3 with lower limit 0, upper limit pi by 2, and cos pi by 2 is 0 and cos 0 is 1. So we will have minus 27 by 2 pi 0 minus 1 by 3, and then if you do the simplification, it will be 9 pi by 2. So the value of this surface integration f dot n ds, it will be 9 pi by 2, the first option. Okay, it's already 7:57. So we are running out of time. I will solve this problem. This is similar, so let me solve a different kind of problem then. So again, here also we are asked to find out the area of this portion of this cylinder between the planes. This is also easy. And the seventh problem, again we are asked to find out this f dot n ds. So I will solve it separately and upload it because we don't have that much time. So okay, let's calculate this one. So it's a different kind of problem. So here we can write this integration as from 0 0 0 to 2 3 minus 6 2x I hat plus 2y j hat plus 2z k hat dot dx I hat plus dy j hat plus dz k hat. So this is the dl, elementary length, the length vector, and let's call it this f of x y z. So then this is basically a line integral. So that is from 0 0 0 to 2 3 minus 6 f dot dl. So now let's say let's see here no path is specified. So how should we define the path then? Because we are asked to do the line integral and we need some path. So the points are, the origin 0 0 0 and the end point is, start point is 0 0 0 0 0 and end point is 2 3 minus 6, let's say here. So now there can be a lot of multiple paths we can choose, like this. So what path should be convenient one, and how can we be sure that all the paths will give the same result? So why we are not given any specific path? It's because the force is conservative, the force field is conservative. So to check the conservative force field, one way is to find a scalar function f of x y z, and in such a way that its gradient will be the this vector field, then the field is conservative. So we can, for this problem, we can easily find out this scalar function, that f is, so this f of x y z is x square plus y square plus z square. If you do this gradient of it, you will get this f. So, but guessing this scalar function, it's difficult. So there is another way, is find out the curl of the force field. So if this curl is 0, so in that case you can say this force field is conservative. And here also, if you calculate this curl, you will see that this force field is conservative. So then in that case we can choose any path to do this line integral. So then what path should we choose? So the easiest path is, so choose path like this. So let's go go along the x axis. So in that case y and z will not be varying, and then go along y axis where x and z is not varying, and then go along this z axis. So there are, let's say this is the path 1, this is the first part, this is the second part, and this is the third part. So when you are on this first part, only the dx integration will be there. There is no variation of y and z. So all these parts will be gone. When we are on the second part, only y integration will be there. There is no variation of x and z along this path. So this dx and dz part will be gone. And while we are on this third part, the z integration will be there, and other will be 0. So in that case, if you do this integration from 0 0 0 to 2 3 minus 6 2 3 minus 6, and it is 2x dx plus 2y dy plus 2z dz, and if we integrate it separately, then 0 0 0 to 2 3 minus 6 2x dx plus 2y dy plus 2z dz, 0 0 0 3 minus 6 0 0 0 to 2 3 minus 6. Now this 2x dx integration, it will only survive along this first part, where x is varying from 0 to 2. So then here we can write from 0 to 2 2x dx plus so this integration will only be non-zero on the second path. So we can write it 0 to 3 2y dy plus, and the third integration will be 0 to minus 6 to z dz. And now if you do this integration, it will be x square, where x is going from 0 to 2 plus y square, y is going from 0 to 3 plus z square 0 to minus 6, and if you put the limit, it will be 4 plus 9 plus 36, which will be 49. So the answer is 49. So let's do another one. Okay, so this is Green's theorem problem. So we are in this square region. So basically we are in a 2D plane, x and y, and we are inside the square bounded by x equals to 1. So this is x equals to 0, this is the y axis, and x equals to 1, this is x equals to 1, and y equals to 0, that means x axis, and y equals to 1, this is, let's say, y equals to 1. So we are here. So that means z is not varying, So in that case, this, so we can write this as let's say closed. So we are asked to find out, we are asked to do this integration in this closed loop. So then set this closed loop, let's call it this loop C, yz dx plus plus xz dy plus xy dz. So now if you see, we are in this always in this z equals to 0 plane, in this xy plane. Z is not varying, so we can drop this term because there is no variation in z. So integration dz, that will be 0. So only these two terms will survive. So in that case, we can write it as yz dx plus xz dy. So then basically we need to do this integration along this line. So we can do that, but the easier way to convert this line integral to the surface integral. So that is use the Green's theorem. So we can term it as p of so z is not varying throughout this integration. So we can put this z outside as a constant. Okay, yeah. So then let's put z outside. So then it is p of xy dx plus q of xy dy, where px is y, and q of p of xy is y and q of xy is x. But you can also put z inside, no problem. So p of xy will be yz and q of xy will be xz. So z is a constant, so we are not writing p as a function of xyz, we are writing it as only x and y. So then if we convert it to the surface integral, it will be del q del x minus del p del y from integration dx dy, and x is, so x in this, sorry, inside this surface x is going from 0 to 1 and y is going from 0 to 1. So x limit is 0 to 1, y limit is also 0 to 1, and if you do this derivative, so del q del x, so del q del x will be z minus del p del y, del p del p is yz, so del p del y will also be z dx dy, which is 0. So this line integral will be 0. So we are already out of time. So here this is a same problem. So you will need to consider this as p of xy, we need to consider this as q of xy, and then apply the Green's theorem. Then do this then this integral will be like del q del x minus del p del y dx dy, integration in this region. Again the region is same, square region, where x is varying from 0 to 1 and y is varying from 0 to 1. So if you do that, you will also get 0. This del q del x, that is minus 1, and del p del y, that is also minus 1. So minus 1 minus minus 1, that is 0. Okay, so we are already out of time. So I will solve these problems. So these are similar, I mean similar to the problem we did in this fast 4 problem. Same problem, same kind of problem. So I will solve these 3 and I will upload it, and so that's all. If you have any confusion, you can ask in the comment section. So if no, then let me stop sharing.